prepared short and slightly perhaps long presentations on our work, but we will go about it. We'll keep it short and brief and perhaps try to bait you into our subjects. And we will share some queries by the by CTE that people had. So we thought it would be a good idea to maybe address the queries in the beginning for 5 minutes and then go ahead with our talks. So the first thing I would like to share is that when starting for or like going for an off-campus thesis, which both of us did, me and Aditya, I'd recommend starting your application procedure early. So BITS, if you have done any projects at BITS formally, you know that BITS is a pre-registration procedure. And similarly, thesis follows a pre-registration procedure, and you have to, and like it's recommended that you start preferably early. So if the second semester of pre-registration happens, for example, sometime around in March and April. So it's a good thing if you start by August with your emailing or other things. Another advantage of starting early is you can take a look at formal programs. Maybe Aditya can explain that a bit better because he took up his internship formally through ICTS, whereas I went the cold mailing route. A second step would be once sooner or later you will hear back from a professor, a postdoc, a PhD student, anyone you write an email to. While there are many things that you might want to discuss, you should have in your mind clear the project topic you want to work on, or at least the specific area you want to work on. Ideally, your mail should contain this in itself if you're applying via cold mail. The second thing you should have in mind is the timeline of your work. So generally, if you're cold mailing someone, the university might not prescribe a timeline for taking on project students. For example, I'm working at ET at Zurich, although my thesis finished sometime last month, and I will continue here till the end of June. And Aditya, I believe, has done the same thing, where he worked on his thesis in one semester, whereas his internship was for a period of 1 year. And lastly, since BITS requires some evaluations from your professor's end, it's best to inform them beforehand. Also, if my voice is lagging or something, just speak up and I'll stop and go back. Lastly, some students asked us about the procedure for registration. You do not have to inform BITS about a thesis. When time comes, you will be sent an email for a PS to TS transfer, which happens sometime in September and March. It does happen twice a year, so that's not a worry, I suppose, I hope. And for this transfer, you will require an approval from your head of department, whichever discipline you're applying in. And yeah, that should suffice. And for his approval, his or her approval, you usually require an offer letter from the department you have chosen to work with. The second step is usually a pre-registration, which is slightly more complicated, but not really a problem either. You'll get emails from AugSD and AGSRD from time to time, and all you need to do by then is make sure you have an offer letter and you have selected a co-supervisor for an off-campus thesis. Yes, an on-campus co-supervisor, of course. Any other queries we can take up after the presentation is done, but I hope this gives some perspective. Right. Before I go on, I should mention that neither me nor Aditya actually are a dual degree student. Both of us took up engineering and did minors in physics and then moved on to physics. So dual degree related questions we can give our best opinions on, or the best we know of, but it won't be a fact coming from us. Right. So my project, my interest was in atoms and molecules in general. And I had taken up my PS1 in the field of computational chemistry, which led me to take up my thesis in theoretical chemistry. And I'll briefly go through each of these terms on the screen right now. Hermann Weyl, by the way, is a rather popular mathematician, but we don't cover most of his works in our courses. He has a great book on symmetry as well. You could check that out sometime. What he was trying to say here is that in a quantum system, as the degrees of freedom increase, the size of your Hilbert space, or in a classical analog, the size of your phase space would increase exponentially. So while a phase space increases linearly as the degrees of freedom increase, the Hilbert space increases exponentially, and hence whole is greater than sum of its parts. Sorry, quite obvious. So this exponential scaling of bases provides both analytical and computational challenges. Analytical challenges are in coming up with a good theory to describe the increasing degrees of freedom probabilistically and accurately. And the computational challenge, of course, is handling all the numbers together. While there are a few and fairly expensive quantum methods which sort of attempt to break down Hamiltonians or deal with bits of Hilbert spaces at a time, a popular set of methods are semi-classical methods, and I want to talk about a subset of those methods today. It's a very niche field, but it's also a fairly popular field. So I'll go ahead with that. You must be familiar with the diagram on the left-hand side. The anharmonic potential shown in red. When you deal with a one-dimensional system, you can express the potential energy as the anharmonic potential for most molecules, as shown here. But when you increase the degrees of freedom and select to plot any two of them against the energy, you get a potential energy surface. Most simulations at room temperature, for instance, can be run using a classical description, wherein we work only with a ground state potential energy. But even simple processes such as photoexcitation and lots of electronic processes, which I'll address later, involve or require the description of excitations in both electrons and nuclei. And although today's quantum mechanics techniques don't cover all of them, on your right-hand side, I have shown a representation of this. So the dotted line and the colored lines are actually just two representations of the same set of potentials. And whether they interact or not is a question of it depends on the basis we choose. But that, of course, is a bit outside the scope of this talk. But it is this interaction between them that interests us and leads to non-adiabaticity. And yeah, let's move on. The technique I've been working with so far is known as spin mapping. This was developed by a PhD student, Johan Runeson, during his tenure at ETH. He's still working here on further advanced methods which build on spin mapping. But let's start with something simple. We'll take a Hamiltonian of perhaps a simple two-state system. And by using linear decomposition of this Hamiltonian, we use the identity and the three Pauli matrices to split one matrix into four matrices. The next step is slightly more complicated. What we are trying to do is sort of think of it as a classical shell around your quantum Hilbert space. This shell, known formally as a representation, is a classical analog of the quantum Hilbert space. What we are doing here is moving from a set of perhaps discrete eigenstates to a set of continuous classical variables. There's a small mistake in equation 2 over here, because this, if most of you might recognize this as a block vector. So you here actually must have spin up and spin down vectors, but I omitted those. So in this two-state system, what we have first done is move from the eigenstates, which describe the Hamiltonian, to theta and phi, which are continuous coordinates on a sphere, to describe the same thing. While I've not explicitly written down the maths here, it will become a bit more apparent in the coming slides. Moving from a two-state to an n-state system, a similar decomposition is first done. And the theta and phi, which were presented earlier, can be further transformed into position and momenta of an arbitrary trajectory on moving on the potential energy surface. While this is a bit hard to grasp without enough visual stimulus, you can think of all x's and p's as a set of trajectories sampled from a Gaussian distribution. This Gaussian distribution allows us to determine a set of theta and phi for each x and p, which in turn allow us to determine the spin matrices and thereby determine the Hamiltonian. And once we have a Hamiltonian, we can go ahead and simulate the dynamics of the system. These two papers here are quite they're quite well explained in this process. 2019 and 2020 papers, the ones I'm referring to, of course. But of course, you can chat with me as well if you like. Anyways, having introduced this fairly complicated process, I want to focus on the two tasks I had taken up in my thesis, or rather in January. The first task was what's the accuracy of this method? And the second task was, can we improve this method? One small thing I would like to point out is that as we decompose this Hamiltonian, you may have noticed that the identity is written separately out of the sum. And that is because depending on the representation we choose, depending on the shell which we build around the Hilbert space, there is a scaling factor which appears outside the summation. And that scaling factor is uniform for all spin matrices. I think that can be your takeaway from this slide before we move on. But that is an essential assumption that we are making of a simply connected symmetry for all spin matrices, which we can sort of investigate more later. Ignore the last equation. Anyways, moving on. The paper in 2020 tested this method on a smaller system of the Fmo complex. For those of you might not be well versed in biology, for instance, the Fmo complex is a simple is a charge transferring conjugated molecule which connects the sort of antenna in the photosynthesis process to the reaction center, allowing the transfer of photon energy from along the leaf. So for this 7-site molecule, or 7 sites being the 7 conjugated loops that you see here, the method worked quite well, but we wanted to extend that to a much larger system, and hence we took up polymers. Here, I have been studying the photoexcitation of polymers for the past 4 months. Of course, I've listed down a few applications here, but I'm sure you must be aware of many more applications of polymers. But the 4 listed here are the ones important to my work, because they involve an initial photoexcitation of the polymer. The polymer we had chosen to work with was polyparaphenylene vinylene. To put it simply, it is a polymer with 2 conjugated sites. The first one is the phenyl group, and the second one is the vinyl group. Here, I'd like to mention that polymers have certain characteristics. First is their long length, and second is the large degree of delocalization they allow for the electrons. These 2 characteristics allow us to study polymers as one-dimensional solid-state systems, of course with some disorder, but one-dimensional solid-state systems. I think it might help to move to a more minimalistic representation here. If you consider the slanted red block as the Finlayne group and the slanted blue block as the Vinylene group, a photo excitation first leads to a localized excitation, which, depending on the energy supplied, may either remain localized or spread over a set of sites. Unless I mention otherwise, I will most likely be dealing in a site basis. For those of you not familiar with quantum mechanics, I'm just selecting the sites as the phenyl and vinyl components as the basis for my vector space. Here we see that the two characteristic localizations can be labeled as Frenkel and charge transfer exciton. Simply put, an exciton is an electron that did not have enough energy to become a free electron and somehow is bound to the conjugate hole that is generated by it. And like the degree of pairing it has determines how far it can localize. Moving from a minimalistic view to a more schematic view, this, like an excitation, can simply be shown as the electron moving to a higher orbital at any given site phi. The Frenkel exciton, however, remains on the same site phi, whereas the charge transfer exciton allows the excitation to another site. This is not quite, this slide is not quite crucial to the presentation, but for any viewers interested, this transfer can take place via either a dipole-dipole interaction through the bond or through a de-excitation-excitation process through space. What happens here is that it forms a pseudo charge transfer state, which might be a bit hard to grasp, but the second one is a bit more visually easy to understand. First, we have de-excitation, a photon is released, and there is excitation on the other end. And we get two charge transfer excitons on the right-hand side in both of these figures. Sorry, two Frenkel excitons. But yeah, as I said, it's not too crucial to my project. However, since we are working with charge transfer and Frenkel excitons together at each and every electronic excitations, it's quite hard to form a Hamiltonian only for the Frenkel bit or only for the charge transfer bit. So here I've presented an ansatz where ignoring the dagger operators A and A, ignoring the operators A and A dagger, you can focus on epsilon n and jn that you should have been inside the summation. But epsilon n describes the energy of a molecule at every site of the chain, whereas J describes the coupling between different sites. So J will tell you how likely an electron is to transfer to another site of the chain at each time step. Yeah. But this, however, does not complete a model. We are still building towards a larger and more realistic model. However, since this is a simple Hamiltonian, we are considering only nearest neighbor coupling. So it's a tridiagonal matrix which can easily be diagonalized. Diagonalizing this matrix gives us a spectrum